Hi, everyone. Thanks for joining us today here at Microsoft Build. We're here to talk to you about Open Federated Learning and how you can build better AI models with your private data. I'm Michael McReynolds. I'm a product manager in the Azure Compute team, and I'll be your moderator today. Joining me for our expert discussion is Mansi and Brian from Intel. I'll pass it over so they can do introductions.
Hi, everybody. I'm Mansi. I'm a deep learning software engineer with Intel, and I work on OpenFL. Over to you, Brian.
Hi, I'm Brian Rogers. I'm a technical solutions architect. And Michael, thanks for having us here today at Build.
Absolutely. And just a reminder, if you've had any questions, please share them in the chat, and we'll work to answer as many as we can. So to get started, Mansi, I was hoping you could share what federated learning is and why do we need it?
Of course. Let me share my screen here. Just a moment. Let me know once my screen is up. Do you see it?
Yes.
Okay, perfect. So thank you, everyone. Let's talk about why do we need federated learning? Well, the conventional centralized learning approach is, for example, you have three data owners. Now, consider these three owners to be hospital chains, and each of them have a local data set of their own. So in conventional centralized learning, what happens is all of the data sets needs to be aggregated at one location, and the model needs to be trained on top of that. But there's an inherent problem with this approach, and that the data could be regulatory by nature. Data could be too large to transmit. It could be bulky. It could be too sensitive. So here comes federated learning in that instead of moving the data to the model, we move the model to the data. So we send a copy of the model to each of these hospital chains which are institutions which have their own local data set. So the model gets trained on each of these data sets. And then these institutions only send back the model updates, which are then aggregated and combined with the updated model. So in this case, the collaborators are the entities that have access to the local data sets, and the aggregator is the entity that sends in the model.
All right, so Mansi, what you're telling me here is we now know that the aggregator has access to the model, which is pretty cool. So you've sent the model down, the aggregator has access, and the collaborators have access to data. But how do these entities communicate with each other?
Yeah, which brings me to OpenFL. So OpenFL is an open source federated learning framework which helps you to train AI models at edge. And let's talk about the OpenFL architecture here. So I said that the aggregator was the entity that had the model. So that's essentially the model owner, node 2 here. So the aggregator has something called the code or the model. But in addition to that, it has also something called the plan file, which basically contains all the hyperparameters needed for the federation. So it has the model, data loader, number of rounds to train your federation on, if you're using any compression pipeline or that, and what tasks to send to each of the collaborators. So what happens is that as the federation starts, the aggregator basically freezes the plan and the model and initializes that and sends that out of band to all of these collaborators. So node 1 and node 3 are acting as collaborators here, which have a local copy of their own data set. We also should know that the aggregator also acts as a certificate authority and grants TLS certificates to all the clients that want to participate in the federation to establish a mutual TLS connection between all. So once the plan and the code are kind of zipped together and sent to all of these collaborators out of band, they then run this using their own local data set. And once that's done, they send it back to the aggregator, just the model updates back to the aggregator, which is then aggregated in this node 2. And at the aggregator, we have a gRPC server connection that starts, and then at the collaborators, we have a gRPC client connection, and that's how they talk to each other.
So Mansi, this is really interesting. I would love if you would give us a demo of how this works in practical reality.
Yeah, of course. Let's jump back to the demo. And with that, let me share. So this is a server that I have up in Azure. I have at this point in time just done a pip install OpenFL and set up my virtual environment. So once you do that, if you do fx-help, you will be able to see all the related commands that we use for OpenFL, and fx is just a CLI that we have for OpenFL. So in order to start the demo, let's assume that the left pane is my aggregator, and then these two right panes are collaborator 1 and collaborator 2. So the experiment really starts with creation of a workspace. So we say fx workspace create -- prefix is just the name of the workspace. So let's call that workspace. And then that you could just choose from a variety of templates that OpenFL has as of now. So you can plug in any code, any model, any data, but for simplicity, we just have some predefined templates that users can choose from. So I'm just using a simple torch convolutional neural network as the model, and then the data that I'm using today is just the MNIST data. So once you'll see that, so this is just setting up all the required, requirements for the workspace. And once you enter the workspace, you will see that we have all of these folders created here. One important folder to look into is the source. So the source is the one is the folder which contains the model. And if you just look into this, you will see that you have the ptcnn.py. So this file is the model that we have. And if you just glance to this file, it's basically just initializing the model, initializing the optimizer, and doing a forward pass of it. So as simple as it goes. And then we also have something called PT-MNIST in memory. And what's interesting to see in here is that we are down, since this is MNIST data set that we're just demonstrating for the tutorial here, we will be downloading this data set from the internet. But then since each collaborator will have its own data set, so to just orchestrate that, we are sharding the data. So each of the collaborator gets its own copy of data, and we assign just shard numbers to each of these collaborators, and then they get their own train and validation data sets. So with that, it's time to initialize the model, which we do with fx plan initialize. And so this is what I was talking about. So if you see, there is a plan.yaml file under the plan directory. And this is so important because it establishes all the hyperparameters and everything that the collaborators would need beforehand. So it has all the required settings that you need, including the model that you're choosing, including the aggregator addresses, and if you're using any compression pipelines or so. To transfer the weights back and forth. And then it also tells you what tasks you'll be assigning to the collaborators. So train and validate would mean that the collaborators, first of all, do a validation over the aggregated or the global model, after which, and report the accuracy, after which they do a local pass of training. And that would improve the model to some extent. And then once they do the validation on that local, locally tuned model, they would be able to report a delta increase in the accuracy. So with that, once we have initialized the plan, let's also create the workspace as the certificate authority to establish, mutual TLS between all of the participants. And for users who don't have a background in, establishing TLS certs, we have a built-in public key infrastructure mechanism called PKI in place. So what you'll need to do is type in fx workspace certify. And what that will do is establish the certificate authority for you. Sorry, I think it's certify. So this will establish the certificate authority for you. So the aggregator is also now acting as a certificate authority to grant TLS certs to all of the participants. With that, we generate the TLS cert for the aggregator. So we do fx aggregator generate cert request. And what you'll see is just generating the cert request, and then the next step would be to certify this cert. So we will use FX aggregator certify for that. And then it asks me if I would want to sign the certificate. I would proceed with a yes. And that's how the aggregator is set up. So moving on to the next window here, let's call this window pane aggregator collaborator 1, and let's CD into the workspace here. For the purpose of demo, for the purpose of simplifying this, we're running the aggregator and collaborator at one place, but the setup would be the same if you even run it on distributed node. So I'm inside the demo, and I would want to request the certificate for this collaborator. So what I'll do is I'll do FX collaborator generate cert request with the name could be 1. And then this asks me what is the data, or what shard number do I want to assign this collaborator to? That could be 1. Okay, and then I go back to the aggregator pane to certify this collaborator. So I do an FX collaborator certify name 1. And it asks me again if we want to sign the certificate. I would say yes here. Okay, and we see that the collaborator 1 is already registered. So we do the similar thing for collaborator 2 here. So we enter the workspace and do FX collaborator generate cert request. And let's call it 2. So again, it asks me for the shard for this collaborator. Let's give it shard number 2. And then let's go back to the aggregator to even certify this one. So I can do FX collaborator certify -n2. Okay, so at this point in time, the trust is established between all of these participants through MTLS, and we are just ready to go ahead and kick off the federation. So at the aggregator node, the aggregator starts through a gRPC server, and for that, I type in FX aggregator start. And what you'll see that it starts the aggregator gRPC server. So on the right pane now, let me start the second collaborator. So I will do a FX collaborator start -n2. And then for the top one, for the rightmost pane, the top rightmost pane, I need to start the first collaborator. So I will do FX collaborator start -n1, and that starts the first collaborator as well. So you see that these collaborators are each, assigned tasks of aggregated model validation, training, and local model validation, and each of them do these particular tasks and report the accuracies or the metrics back to the aggregator. And round after round, you'll see there's a delta improvement in the accuracy that's being reported here.
Now you mentioned earlier on though that a couple frameworks were available. Like, so when we talk about them, like what frameworks are you talking about? What's available to you?
Yeah, so OpenFL is completely framework agnostic, meaning that you could plug in any, data set or any model. You could have a PyTorch, Keras, TensorFlow model. We even have support for JAX, doesn't matter. So you can plug this any framework. It's totally framework agnostic.
And Mansi, keeping the data and the model private is super critical. Do OpenFL use any privacy preserving ML techniques?
Yeah, of course. Let me get back to the slides here that I could share. So let's talk about security and privacy in OpenFL. Now, we've been using technologies like Intel SGX to run our applications inside hardened enclaves through Grameen. But apart from that, there are other, privacy-preserving machine learning algorithms that we could use and that we have with version 1.5 that's been launched. So we have global differential privacy, where after each of these collaborators just train the model and send the model updates back to the aggregator. Just before that, the model updates are clipped, and then at the aggregator, white noise is added, so that these collaborators are differentially private with respect to each other. We also have something called ML privacy meter that quantifies the model leakage from the model updates. And then for the model owners who want to preserve their model and detect a malicious collaborator who is changing their model, they could watermark this model. So we use waffle algorithm for that, and model watermarking is one way we could preserve the model IP.
This is super cool. Could you share a little bit about the integrations that we're doing with OpenFL and the Microsoft CCF?
Yeah. So we are glad to announce that we will now be soon we'll launch a security add-on repository for OpenFL called OpenFL Security 1.0 that leverages Intel SGX with Microsoft CCF and has an entity called the governor, which basically manages the participants. It can manage the data sets, it can verify the plan, and like help in supporting concurrent federations. The collaborator and the aggregator code are being leveraged from OpenFL, but they are now being used inside hardened enclaves using Intel SGX. So that it goes on to say that whatever is being run within these hardened enclaves will be encrypted and will be secure. And then to verify what's running inside the enclaves is indeed what's supposed to run, we also have a feature. We also support remote attestation through the use of attestation verification service.
So earlier today too, we even heard from Arun Gupta and Graham Barry about some of this, where the CCF is really coming in. This is a great place that we're collaborating for, and it's also a great opportunity for the community, I think, to get involved if they have any other inputs they want to make sure that the security is being handled properly. I mean, that's what I'm understanding anyway.
That's right.
Awesome.
And then, I could just have this page on, so you can check out OpenFL on GitHub. You can either type in openfl.io, and that's our OpenFL page. You can even pip install from PyPy or use it through Docker Hub.
Great. And then we do have a couple places we've used this so far, right? I mean, this it's not just slideware, and it's not just some vapor demo, right? You got something real for me, right?
Of course not. No, for sure.
Okay.
So OpenFL, Intel and University of Pennsylvania have jointly completed the world's largest healthcare federation study that leveraged OpenFL, and they studied the MRI scans from over 6,000 patients across 7 locations, and 6 different continents to find malignant brain tumors. And what they found out was, using this unprecedented data set, they could demonstrate an improvement in the brain tumor detection by 33%. And this goes on to show that not just the volume of the data is important, but also the diversity is so important for the AI models to generalize well. And we also have something called FETS Challenge that we host every year around brain tumor segmentation. And we also have OpenFL is also being used by NASA's Frontier Development Lab to study the effects of radiation exposure on the astronauts, because the data is private, and the cost of transmitting data that could be generated aboard a spacecraft it's so high.
So, and when I'm thinking about this, I mean, I served a previous life around HIPAA, and I did some stuff around the government. I mean, we're looking at, I think, Michael, to your point earlier, it was the chain of custody, making sure that that model is safe and secure. I mean, now we're talking about HIPAA compliancy, meaning you folks have worked around the HIPAA compliancy problem, saying that if we send the model down and you have your data secured, you can go and get data that, by the way, we can't do underneath normal regulations. Passing around paperwork and patient information is not good. But now, since we're not passing that and we're just learning from it through a secured environment, it looks like we're able to really kind of jumpstart the industry here of being able to share global information for global patient sets, right? And then I think, exactly, Michael, what you're kind of like referencing is like, let's make sure that it's secure too. That model's not then further edited by some outside untrusted party.
Absolutely. And the development of these models is pretty substantial when it comes to the research and development costs. And so you want to absolutely protect that intellectual property. Mansi, would it be possible for you just to flash back to how our audience can get started with Open Federated Learning?
Of course, yeah. So as I talked before, there's a GitHub page that an OpenFL is completely open source community-driven project, and we've recently moved to LF Data and AI to increase our federated learning community. So please check out our code there. Feel free to add in PRs, issues, whatever you feel like. Try OpenFL using your own code and data, and that's about it.
Okay, perfect. Well, thanks so much, everybody, for attending the session today. Please check out the links that we shared, and we'll catch you again. Thank you.
And any questions? Do we want to take a quick question here? I see something coming through.
Actually, yes,
Maybe
we do.
Yeah, let's take a quick question.
Okay.
So the question is, it seems like TEEs are being used for aggregators here. Some other frameworks like Secretflow seem to give some optionality here and have support for SMPC or HE, homomorphic encryption as well. Are there plans to add support for those privacy enhancing technologies at the OpenFL, or is the view that the OpenFL team, that TEEs and differential privacy in conjunction with federated learning are sufficient? Mansi, do you mind taking that?
Yeah, of course. So I have my view on that. I think we've been trying to expand, security and privacy through the use of SGX, and I don't think that's going to end there. So of course, the answer is they are not sufficient, because even though you add in as many privacy preserving mechanisms, you still have some of the other attacks on model or data. But as to whether we have a short-term resolution or support for other frameworks, I don't see that in the pipeline yet. Prashant, do you want to take a quick jab at this question?
And while Prashant's doing that, maybe we can start going and answering the second one, because I think Prashant can only answer in the chat there. So the other one was,
Okay.
I'm wondering how I can make interpretations of the model results if some of the data is encrypted. I think that's a good question. If I'm understanding it, this is, well, you've done this run over there. How is it real? How is that data real, and why?
Yeah, so first of all, whatever is being run inside the enclaves are all encrypted, but then at the same time, we have remote attestation to verify that it's supposed to run what it's running. And then the results of those are always sent back. So the results would be sent back to the user, or would be available at the aggregator side. But then you have policies in place to verify whether what they're running is indeed what they're supposed to run.
Sorry, if you can dig in on what do you mean by policy there? Like, is there like a
So we
certain
use
framework?
so for OpenFL Security that we're going to launch soon, we basically use attestation verification service, and that helps us. So it has the measurement of the enclave. So if that means that if you try to add in or remove or change anything inside the enclave, or any code that's running inside the enclave, that would change the MR enclave value, and that would mean that essentially that participant gets kicked out of the federation, because they are no longer running exactly what they're supposed to run. So the hash is verified every time an application is running inside SGX.
So if I'm understanding, the attestation we're talking about is also something that we spoke a little bit about today. Is, I mean, so we have what could be cloud specific attestation that Azure provides, but we also have non-cloud specific. So if we want to get really down to the dirty, then now that we're in a global federated environment, that we have attestation that we can have as a third party zero trust environment, we're working on it. I think, Michael, are you folks involved in some of that too? I believe with that zero trust environment.
Absolutely. We provide SGX. We've provided it for a number of years with our Coffee Lake instances, the DSFP02, and last year we increased our footprint with the launch of Ice Lake and the DSFP03. We also offer support for the Microsoft Azure attestation service, and we're partnering very closely with Intel for operator independent attestation with integration with Project Amber, We've also been working really closely with Intel on Intel TDX. We just recently released a preview of TDX. We didn't cover it much in today's session, but we have a very close partnership with Intel on a number of these technologies, and we look forward to continuing to invest in that relationship.
It's awesome. Folks, I think we're good now. I don't see any more questions. This was awesome. Thank you for your support. And I appreciate your time.
Absolutely. Thanks, everyone.
Thanks, everybody.